So thank you for Panagiotopoulos. We're going to continue for the third installment. It's very nice and I think very interesting series of talks. Thank you. On the definable content of cohomological invariants, the third part now, theory and examples.
All right. Hi again. So yeah, this is the third and final part. I had a different plan for this talk, but it turns out that there were some natural questions here, and I thought maybe to change a little bit the topic. Still, I will cover applications like examples like homology, but I will put the weight in a different place, I think, which is explaining a little bit why the theory works, and then do some examples like homology. So. Right, a reminder that this is based on a joint project with Martino Lupini and Jeff Petco. And we have seen some things here, and I'm going to talk a little bit about X today also. And then I'm going to switch and talk a little bit about here a Czech is missing, Czech homology. So I'll talk a little bit about that. Right. So a very quick reminder, like where we stand. Right, so the whole idea behind this project is to take various invariants, classical invariants from either algebraic topology or homological algebra, and refine them, add some additional structure, which I explained more or less what the structure is, and turn them into their definable versions. And how do we do that? Well, the classical invariants, when we're talking about classical invariants, all the invariants on the left-hand side in the previous slide are constructed either as homology groups of chain complexes or as cohomology groups of cochain complexes. So one starts with a cochain complex of abelian groups classically, right? So every object here is an abelian group, and every map here is a homomorphism. And the fact that this cochain complex means that if you compose two consecutive arrows, you get zero. This is by definition what the cochain complex means. This means, in particular, that the image lands inside the kernel of this map. So I can divide them, and this is what the cohomology group is. Right, centered around N here. I have one map whose kernel I take, and I have one map whose image I take, and the nth homology is the division centered around here. Right. So now the point here is that what we want to do and what we actually did, as a matter of fact, what we thoroughly explained and we saw some how this object behave is that to turn them into definable invariants, we have first to check that the constructions that out of the objects that we care, we take. So how it works? We have these objects, and from the object we associate some chain or cochain complexes, and from this chain and cochain complexes you get the cohomology groups, right? But the point is that starting from a collection of objects, the chain and cochain complexes often carry some Polish topology, and I will see some examples today. What is this topology, right? And once you have this Polish topology, then the definable, then the homology and cohomology groups can be thought as groups with a Polish cover, and the maps are what we call what we termed definable homomorphisms, right? So yeah, so the setup is like that in the definable context. You have this cochain complex that these groups are not just groups, but have a topology which makes them Polish groups. And the maps are, well, they have to respect the topology, so they are just continuous, right? And the homology group here, we don't view it as an abstract group, but we view it as a group with a Polish cover. In particular, the maps are definable homomorphisms in this category, right? So we move from the category of abstract abelian groups with abstract homomorphisms, the category of groups with Polish cover and definable homomorphisms. And when we do that, we get finite invariants, and we gave an example already that, for example, definable homology, which I haven't defined, but more or less we saw with what groups are involved. There are these p-adic integers mod G as abstract groups. This definable homology classifies solenoids out of homomorphism, while standard homology, which is the classical version of it, where we start from and then we enrich with definable content. The standard homology cannot do that. In fact, there are uncountably many pairwise homotopy equivalent solenoids. Right. Okay, so this is just a reminder of what we covered so far. What I want to do today is two things mainly. It is, first of all, I want to convince you that the categories involved, and there are essentially two categories here, as when you do homological algebra, at least at the beginning. The first category is we have spaces. From spaces, we go to chain or cochain complexes. So here you have a category, and then you go to homology and cohomology groups, and here you have another category, right? So we'll talk a little bit about what is a cochain map in a bit, but there is this category of Polish cochain complexes, let's say, with continuous cochain maps, where we want to basically see that this category behaves well. So various constructions that are very important for algebraic topology and homological algebra can be performed in this context. And it interacts well with the category that we've been discussing so far, which is group that was covered with definable homomorphisms. This is one thing, and then what I want to do is to provide some examples of how concretely one passes, by example, how you take various classical invariants and you turn them into definable. So how from the objects, when you form the chain complex, what is the Polish topology that you put there? Right. So let me start with the first task. Right, and how homological algebra works in the definable context. And let me remind some definitions. So, okay, so let me be here a little bit more general, right? So generally, when you do homological algebra, you don't put zeros here necessarily. What is a cochain complex? It's just a sequence of homomorphisms here, because we are in the Polish context. This will be Polish abelian groups, and this will be continuous homomorphisms, right? The fact that it's a cochain complex by definition means that when you take two consecutive co-boundary maps and you compose them, you get zero, right? In other words, as I said, this means that there is this quotient here that can be defined in its coordinate, which will serve as a homology group, if you want. But okay, so now you may have what are the maps between cochain complexes? Maps between cochain complexes. So you have a cochain complex like that, and another cochain complex like that, and usually what a cochain map is, without the continuous yet, what a cochain map is that a group homomorphism on its vertical direction, so that its squared here commutes. Its squared here commutes. The square commute means this identity holds, right? Well, since we're working with Polish groups and continuous maps, we just ask for this vertical maps to additionally be continuous. This is the only thing we ask, right? Okay, so now it's a fact that whenever you have since whenever you have a cochain complex, you can associate to its coordinates some cohomology group. You have a cohomology group, let's say, based here, and a cohomology group based here. And this map here induces a map between the cohomology groups, and this is because this sort of squares here commute. So the nice thing about cochain maps is that they induce maps on the level of cohomology. Okay, and here's something that you want to do when you're doing homological algebra. This is like the bread and butter, let's say, of homological algebra. Is that in the classical setup, before we talk about the definable setup, one may start with a short exact sequence of cochain complexes. Now, let me remind you, whenever I'm saying exact, what do I mean? So, if I have, let's say, an object here, A, B, C, and here let's say this map is F and this map is G. Exact means that at its level, at its coordinate, for example here in B, what I have is that the image of F is exactly equal to the kernel of G. This is what exactness means, right? And now in a sense, remember that when we're talking about cochain complexes, we don't ask something so strong. What we ask for cochain complexes is this. And then we divide. Well, for exactness, we want this stronger thing. In some sense, cohomology groups measure how far this cochain complex is from being exact. This is what the cohomology groups measure. But exact. So this is what exactness means. Exact. Okay. Here, this might be groups. Here now we don't have groups. We have cochain complexes. So when you unravel what this means, take this and put it vertically. It means that on its coordinate, this sequence is exact, this is exact, this is exact, this is exact, right? So you see, you do homological algebra, some algebraists write down this little thing, and what they mean is all this, right? And it gets some time to get used to these things, but they're convenient. Okay, but right. So here I haven't spelled out what exactness means in this particular setup, where you don't have an infinite thing, but you have something finite. You start from 0, you have a group, and 0 again. Exactness around B0 means this, the thing that I wrote here. But exactness on this level means subjectivity, right? Because the image would be the kernel, but the kernel is everything. And on this centered around here, it means subjectivity, because you know the kernel is the image, but the image is just one thing. Right? So here I have just spelled out what short exact means. So whenever you have a short exact sequence, there is a lemma that tells you that this induces a long exact sequence of the associated cohomology groups. So you see around here you can form a cohomology group, and here you have a cohomology group, and this map induces maps between the cohomology groups. This is, let's say, this map. And here, and here, this cohomology group associated with that, and you have a cohomology group associated with that, and this map induces a map like that. This map. But here there is this weird map. There is this weird map that when you reach here, it allows you to go back to you go one dimension up, one dimension higher, and here you meet again the cohomology group of A. So there was A, B, C, and then there's some sort of discontinuity here. You jump back to A, and you increase one dimension. So this comes out of, well, in the beginning, when you first see it, it's just homological nonsense. But actually, there is some method to the madness, and this method to the madness is called snake lemma, right? So there is this scene in this movie where, well, she explains exactly what the snake lemma is, and this is what we're going to do now a little bit. I'm going to remind you a little bit about it. Instant Mr. Wrong. Okay, so here is what how the snake. So okay, so we don't need all this data that I have there. What we need here is something much smaller. So let's remind ourselves. So here, let's say now I have flipped the previous diagram, and I have taken a slice of it. So here I have this short exact sequence, this short exact sequence, and I have these maps here that these diagrams commute. This is what I have. Right? Now the snake lemma tells you that look at this map gamma here. This map gamma here has a kernel. This kernel is a subgroup of C. It tells you from this, not from the entire C, but only from the kernel of this map, which is a subgroup, right? From this kernel, you can construct a map which is a homomorphism that doesn't land. It's not a homomorphism when you map to A prime. We will define a map going to A prime, but this map is not going to be a homomorphism. It's going to be a homomorphism after we divide with the image of A. Right. So this portion here is called the co-kernel of alpha. Right. So basically, it tells you that. So here you have the kernel of alpha, the kernel of beta, the kernel of gamma, and the map F restricts to a map between the kernels. But when you reach here, there's a discontinuity that takes you back here. So how do you prove such a thing? Well, it's not very difficult. Let's start. We'll start with an element here. Let's start with an element C here in C, which is in the kernel of gamma. So this R going to 0 is not the same as this. C is in the kernel of gamma means that when you map it that way, you go to 0. But the fact that C maps to 0 that way, it's trivial because there's nothing here except 0. But I'm placing that here just to remind you that whenever you have exactness, and the sequence above is exact, it means that everything that is in the kernel of this map is in the image of this map, which means that there's something here that will map to C. In fact, there may be many things that will map to C. I have to choose one. Okay, once I chose one, now there is a natural direction now I can use this beta here. I can push what I chose down. So I push it down, and here's the cards. Now this C being in the kernel of gamma means that this C, when I push it down, goes to 0. This C goes to 0 that way, right? So this means that this bit that I chose, if you go that way and that way, I go to 0. But because the diagram commutes, it means that if I go that way and that way, I go to 0. This means that this goes to 0. And because this goes to 0, it means I can lift it up from exactness. So this map here, so from I started from C and I managed to reach some A prime in A prime. This map, of course, I had to make a choice here, and this choice somehow doesn't allow me to say that the map from the kernel to A prime is a homomorphism. But when I mod out by the image of alpha, it turns out that it is a homomorphism, and this needs a little bit of checking to do. Right? You use the rest of the diagram. So we haven't used commutativity here, for example. You have to use certain things to show that actually that this is homomorphism. But the important thing is that while I was building this map in all these directions, well, some directions were natural. Here I pushed down. So for example, if beta is a continuous map, this is a continuous arrow. However, this going about this unnatural thing, choosing something, is not necessarily continuous, right? So this means the following thing, that when we work in the definable context and we want to from here come here with a Borel wave, we have to make sure that this is chosen in a definable way, right? This my point is what you have to remember from this slide is this, that there is some unnatural choice here, and so there is some work. There's some work that needs to be done to show that, for example, this thing and this thing, but the difficult thing is this part, that this can be lifted in a Borel wave. Yeah.
Do you need to use the fact that F or F prime are injective?
So
So the fact that F prime is injective makes it easier to argue that this here is Borel.
Yeah, but in the other case, you only have the continuity condition where they are not group homomorphism. So the kernel being 0 does not imply necessarily that the functions are going to be injected, right?
So here this function is going to be injective.
Yeah, but this is the classical setting, right?
Yes, provided the classical setting, yeah.
The other setting that you were proposing, those functions that were down, you only assume that they are continuous.
No, they have to also be injective here. The definable setting, it looks exactly like that, with the only difference that these groups have a topology, and the maps are on top of that, they are continuous, but they have to also be injective. Yeah, yeah, you're right. Remember, I wanted to say things about two different categories. One category is the category of Polish cochain complexes and cochain maps, where here I'm not working on some quotient yet. You're right. When we go to the quotient, then more care needs to be, yeah. So here we don't have like Borel lifts yet, but you see here that this is already starting to look like here's the first quotient that appears. Right, and the point is that okay, so the lemma is that you can actually do that in a definable way. You can do that in a definable way. In particular, you see, I have this quotient here, and the map that I was given from this snake lemma has a Borel lift. So Borel lift, well, on the right hand side, I have the same group. I have the kernel, which is a Polish group, and here A prime is a Polish group as well. I have this map, which is not a homomorphism, but it is a Borel recipe implementing the snake lemma, right? Yeah.
sorry, just to clarify, so this map that you're going to get from the kernel of G to the
Yeah, this one here.
this one, the co-kernel. Okay, so that's not going to be like continuous or anything. It's going to be definable. Or
It's going to be Borel. Not only.
Oh, okay.
Right. Well, the map from here to the co-kernel. Here, haven't yet explained what the topology is. It's a quotient thing, right?
Yeah.
What I'm saying, it has a Borel link. From here to here is an abstract. It's an abstract.
I realized my question was that, like, at the level of homology, this is going to be like a definable.
Yes.
Yeah, okay.
The fact that it's going to be definable map comes from what I'm on this slide. Right. This is why I won't count the Borel link. So now it's definable. Right. Yeah. Thanks. And this relies on this lemma, which is sort of a classical lemma. It tells you that here it's not a group with a Polish cover, it's a Polish group. It tells you that whenever you have a continuous homomorphism between Polish groups, then you can find a definable section, so a Borel section going the other way around. Right. So if you wish, let me. So here I want to take a little pause and explain this a little bit, because I think it's. There are certain lemmas that appear again and again when you do, let's say, distribution theory or dynamics of groups, and because they appear often, this means that they are more important than other things. So things that are important, it's good to repeat them. So let me. So I have here, let's say, I have a continuous group homomorphism, and let's assume that for simplicity, that for the exposition here, that this is surjective. What I want to prove this lemma is I want to find a Borel map going the other way around. This Borel map is not going to be a homomorphism, it's going to be just a selection. It's going to be a selection. Right? But if you think about it, so the first ingredient here is to consider for every Polish space, you can consider a new space which has a nice Borel-Sim algebra. This is the space called closed sets, the hyperspace of all closed sets. Now, selections are not canonical, but what's canonical here? I can take some X here and map it to the pre-image of the singleton X. Right? What is this going to be? This is going to be some coset. This is going to be coset of the kernel of the map. And because the map is continuous, the kernel is a closed space, and translates of this kernel are closed. So I have a natural map going that way. And then what I want to do is that from every closed set, there is a lemma that tells you that whenever you have a closed set, well, so here's what the lemma tells you. So the lemma tells you that, let's say, if X is Polish, it tells you that there is a selection map. Let me use a different letter. Let me tau, let's say, from closed sets the space which is a selection. And this is Borel. This map is Borel. Of course, if I have to prove such a thing, I have to explain what is the Borel-Sim algebra here, right? But so when you see that for the arbitrary space, it doesn't look so obvious how you're going to make the selection. However, if we come here at the best space, so often in descriptive set theory, a lot of things you can transfer them to the best space. These are called transfer theorems. And the reason is that every time you have a Polish space, let's say, for example, the group G, there is a continuous surjective map from the best space, which is this line here, on G. And because it's continuous, for example, every closed set can be put back to a closed set here, right? So the best space are all infinite sequences of natural numbers. Here is one. And I can truncate it. I can see the first coordinate, the first and the second together, the first, second, and third coordinate, and this will give me this path. In this tree consists of finite sequences of natural numbers, right? And now this selection is a little bit weird when you see it in the arbitrary space, but when you try to figure out what the selection is here, it's very easy to see. The reason is the following: if you give me any closed, so the best space is just this. This that sits above, and you can think of it as a bookkeeping device for Kloppen sets, if you wish, right? So here there is this sort of correspondence. If you give me any closed set here, this closed set corresponds to what we call the body of a certain pruned tree. So there is a tree here, a subtree of this tree, that all its infinite branches correspond exactly to F. So this corresponds to, we denoted like the body of the tree. And this tree will be collect all vertices that have some branch that hit F. If you collect them, just on the basis that F is closed, it turns out that every branch from them will land inside F. So you can say to each closed F a certain tree. And now, how do you choose something? How do you choose a point inside there? Well, there's a natural way to do that because each level is well ordered. You can choose the minimum, so you can choose the leftmost branch. So in the first place, you have a canonical selection. You just use the leftmost branch, and by this transfer theorem, in a Borel way, you can use this principle to from the closed sets here to go up here and select. So you perform the selection there, but by the transfer theorem, you pull it back, and you can so X goes to this closed set, and here you use this principle to select a point there. Right. So this is just very brief explanation, intuitive explanation as how these arguments work in descriptive set theory. Yeah. Sorry if this is nonsense, but I'm just trying to give like the bolts and.
Does this mean that it is some kind of order of the bare space that we're exploiting here, and is this special just the bare space?
Right. I think it could be the lexicographic order. Is it that order? Right. At this level, so here here you have the natural numbers, and you can take the minimum out of the branch that are represented. So for this tree, there's nothing using a zero, but this is the smallest. Now you go to the next, and here you see out of the next node what is the smallest. So yeah, it's the lexicographic, I think, order, no?
Sorry, I hate to ask an obnoxious question. So here there's like an obvious sort of, well, not maybe an obvious, but like a natural choice for general Polish spaces, and choice for that?
No. If you don't need choice, the point is that whenever you have a Polish space, there is a continuous map. There's a continuous map from the first space surjecting on X. So the closed set you want, you can pull it back. It will become a closed set here. Here you can use this construction with Borel to pick select, and then the map you'll use back to.
Yeah. Okay.
Back.
Sorry, I missed the.
Yes.
Right.
So this order, when you put it on G, does it become like a pre-order on any Polish space?
Right, because this map is not going to be injected, it's going to be subjective, so there's going to be some collapsing. But yeah, I guess.
So people look at the pre-order in Polish space.
It's just, I don't know. Yeah, that's a good question. Yeah, I haven't. Generally, there's often people use also, for example, a trick that people often do is that you can often you cannot well order definably a Polish space, but you can linearly order it by, for example, Borel isomorphing it with the reals. So they have used, this is a trick that people use to transfer orderings, but I haven't seen this particular order being transferred. Okay, so this is on the level of the first category, the cochain complexes and cochain maps. And here the point is that you have to use some descriptive set theory to be able to show that what you expect works. This theorem is not very difficult, like this lemma is not very difficult, but here is something that may be a little bit more difficult one may have to use. So let me go back, and this is a question that also Chris asked me when I first discussed this. So let me remind you what is the definable isomorphism of groups with the Polish cover. So now we go to the category that we are more familiar with because we have discussed a lot. These are now groups with a Polish cover, right? So a group with a Polish cover is just a quotient where G is a Polish group and N is a Polish normal subgroup of G. Right. And here, if you remember, when I defined what a definable homomorphism means, but also I discussed what a definable isomorphism means. And a definable isomorphism, what I said it is that it's an abstract isomorphism of groups that has a Borel map as a lead. Right? Of course, if this is an isomorphism, you can invert it on the level of the quotient. And the question is, does the inverse also admit a Borel lift? Right? Because you see, when you work in the category, of groups with Polish cover, there's an abstract categorical way to say what isomorphisms in this category are. And you would like isomorphisms in the categorical, well, isomorphisms in the categorical sense will have to have this property that their inverse also Borel lifts. And it turns out that this answer is yes. And it's from a theorem of Kekris and MacDonald, which is, well, in a little bit different context, we have to transfer it here. So as a consequence, we have that a definable isomorphism in this sense is the same as being an isomorphism in the category of definable homomorphisms between groups with the Polish cover. And this relies on a little bit, well, a little bit more difficult results from descriptive set theory, which are called large section uniformization results. And what I would like the next slide to do is to just give you like a little bit of a glimpse on what these results are. Right? What are these uniformizations? These appear again and again, these uniformization results. So so here is the picture that you can forget about groups with the Polish cover. Now let's work in this setup. So here we have X is a Polish space and Y is a different Polish space. And someone gave me a Borel set here, Borel set. What I would like to do is I would like to find a section from its projection up, meaning, so we say that this Borel set admits a Borel uniformization. If you can find this a subset of B, so that in its vertical slide you have only a single point, right? So this is for every X in X. If there is, well, if the fiber, the B fiber is not empty, then the S fiber has exactly one point, right? Another way to say that is that S is the graph of some Borel function, which is partially defined only in the projection of B. And here's the first question. Well, the first, I guess, it's not I have phrased it as an answer, I guess. So there are Borel sets that do not admit Borel uniformization. The point here is that there are Borel sets whose projection is analytic. If you have a Borel set, there are Borel sets whose projection is not Borel. Right? It's what we call analytic, not Borel. In that case, you cannot find uniformization because one projection of Borel set is not always Borel. If this projection is 1-to-1, then it is Borel. So if you could find if this projection was not Borel, but you could find the uniformization, then this projection would be the projection of a 1-to-1 projection of this S. So just from the fact that there are Borel sets that project to something that is not Borel, you can see that there are that not every Borel set admits uniformization. However, it's a bit more tricky. This is not the only problem. So there are Borel sets that project to Borel set, and still you cannot uniformize. And maybe this is a little bit more descriptive set theory than you would like to know, but it's not going to take me long. So let's say here is your space X, and what you can do. This is like something I'm not going to prove, but these are the sort of separation properties of analytic and co-analytic sets. So there is a well, let's say here, for example, maybe this is a 0-1, doesn't matter. You can find two sets, C0, C1, which are what we call co-analytic. So these are complements of analytic sets, so complements of projections of Borel sets, and they are disjoint, and they cannot be separated. They cannot be separated by any Borel set. So you can separate it means to find here something that's Borel and contains one, but it's disjoint from the other. You cannot find a Borel separator. Well, once you have that, and you know a little bit more descriptive set theory, what you can do is that you can use here the bed space, find find a closed set that projects to the complement of that. This is analytic, the complement is analytic. You can project a closed set on it. So you can find here this is a closed set that projects to the complement of this. Right? And you can do that for the other side as well. So here you can like do it disjointly above these things. So these things together, they're closed. Their projection is 0, 1, covers everything, because these two are disjoint. So these project to the complements of them, so they will cover everything. And here it turns out that this set does not admit, this is a Borel set, it's closed in particular, but it does not admit uniformization. This is a trick from Blackwell. Okay, so the situation is messy, right? But here's the important fact, and this is what it's often called as a uniformization with large sections. If you have a Borel set so that its fiber is large, what does large mean? Means non-meager. Then you can find the Borel uniformization. So, and the reason why this is the case, if you think assume that the vertical space is the bed face, right? And look at the fiber. A fiber will be some set, not closed necessarily, will be some set here, which is non-meager. If it is non-meager, you can sort of construct a tree. What's the tree? It's the tree with the most heavy branches, right? You put a vertex here. Let's say this vertex belongs to the tree. If everything below is non-meager, and this tree will be keep track of not of the entire set, but of these heavy parts. And the point is that once you have this tree, you can use again the mean, the leftmost branch, and as the sections, as you move on sections from left to right, this tree that keeps track of the most heavy parts of the slices that doesn't change very much. So you can do the selection in a Borel way. All right. So I don't want to spend more time in descriptive theory. I just want to convince you that there are some heavy theorems that are involved when you're trying to prove these things. But once you have proved them, the point is that these categories work nicely, right? And maybe what I want to leave you here with, at least for this part of the talk. Finally, maybe this is the question that is behind our minds since the beginning. Why is this polisability assumption on the kernel? Right? Remember, this map here, we can list it to the Borel map, and now we want to find an inverse. Finding inverses is very similar to this problem here. This problem here. And so what we want to do is when we want to make our map land, we want to have a nice notion of largeness to be able to talk about things that are not small. Right? So now if when we want to land our fibers are polisable, this means that they have an intrinsic notion of largeness. And we can use this notion of largeness to produce this sort of definable inverses. Right? So I guess all this discussion here, which made no sense, at least it went somewhere. This is what I'm trying to say. Start with. But polisability is important. It is what makes this sort of category work well. Right? You cannot remove that and expect, for example, that definable isomorphisms will be the way I define them will be the same as the categorical notion of isomorphism if you remove polisability. Okay, so let's now move to some examples of how you take a classical cohomology theory, and to it you associate, you extract some Polish topology, right? So we're done with this theory. And maybe I wanted to have here an example from algebra and one example from topology later. I think time is running, so I'm not sure how much I'll be able to talk about topology. But maybe we can cover this example slowly here, okay? So, okay, let's start with the two countable abelian groups, B and F, right? And an extension of B by F is a short exact sequence like that. So B is given, F is given, and you want to try to find something in the middle that surjects to B, but it has, when you look at the surjection, the fiber, the kernel, looks like F, right? So the letters here are not chosen by accident. B stands for base, and F stands for fiber. Right, and whenever you have any two abelian groups, B and F, there is a natural thing to place in the middle, always. So whenever you have some fiber here given to you and some base, you can always fill that here with something to make this exact. We can just take the direct product, direct samples, right? Oh. Right. If B looks like that and F looks like that, this looks like that. So this projects, and if you take the zero here, the kernel will look like the fiber that has been injected. Right? But the point is that this is not the only way to do it. Sometimes it is, but it's not always the only way to do it, right? So we may have two extensions that are very different. So what do we mean by that? Well, two extensions. So this is one extension, the other extension. We call them to be isomorphic. We say they are isomorphic. If you can find an isomorphism that preserves the fiber and the base. So these two triangles commute. Right. And you can spend some time here trying to think examples. Here is one. So let's say you look at the group with two elements, and I'm going to put that here. And I want Z to be the fiber. And here are two extensions that are not isomorphic. Right? One of them is what I presented on the board. It looks like a product. The other is to take here times two. Right? So times two, and here you mod out. So these two are two extensions that turn out not to be isomorphic. And one would like to classify all these extensions. And this is what this group X does. So these are some old results, but very inspiring. It turns out that if you abstractly view these extensions as, you can view all these extensions abstractly as elements of a group themselves. So the identity of this group would be this trivial extension. What the multiplication will be, it's a little bit difficult to describe, but it will come more or less from what I'm going to say here. Right. So this group we denote it like that. These are all extensions of the base B by fiber F. Right. And this group is nothing else but the one-dimensional homology group of a certain cochain complex. So what is the cochain complex? So we'll focus on the center will be this here. So the objects in this cochain complex are groups of this form. So these are all maps, not homomorphisms, all maps as separated maps with from B to F. Well, F has the group structure, but B we view it as an indexing. And here P times B, it's like a collection of indices. We look at all maps from here to F. But this is a group because you can pointwise add, right? You can use the group structure of F to add pointwise. Now, okay, it's easy to describe what well, I can describe what the delta 1 is, and then delta 2 becomes a little bit too complex to write down. It doesn't matter. I will throw this here. It doesn't really matter at this point what these things say here. What matters perhaps is the intuition. So we're trying to describe extensions, and the point, what is the point? The point is that this kernel will each element of the kernel will describe for us some extensions, but there will be descriptions, two different descriptions or many different descriptions that will be descriptions of the same thing. And these two things will be descriptions of the same thing if the difference is in this image. Right? And how do you think of, right? I mean, if you try to follow up the algebra here, it may take time to realize why this works. But one way to think of it, here's the idea. Let's say you have this F and this B, and you are trying to describe this extension, but you want to describe this extension without any reference to E. You can refer only to B and F, right? You are not given E. Well, in this particular fixed example, you are given E, but in general, you would like to describe it without reference to E, but with reference only to B and F, right? So if you wanted, you could do. So you have the here B, and here is E, right? So, and here these are the fibers. What you could do is that you could choose some section here. This section is not going to be a homomorphism. It's going to be just going to choose from each fiber a point. Assuming that I have such a section, I can describe multiplication, how multiplication works here. I can describe how multiplication works here. What's that? I can describe how multiplication works here with using a map, which this map looks very much like in the second bullet. Right. Right. The point is that if you give me some, what is my notation there? It's x and y. So I have some x and some y here. And I have 2 points in these fibers that I want to see how they are multiplied, right? I look at the difference. I look at the difference from the representative, So I can write this as my representative Sx plus something from the fiber, let's call it F1. And I can write this as my representative Sy plus F2. And then when I add them, I will land to the fiber of x plus y. I will land here this fiber, and I will get something which is going to be some amount away from the representative. So this will be plus something, right? And how these things are organized, is given by this map C. Now the point is that if I choose a different section, a different S map, this will give me a different C that describes the same extension. To account for that, you have to say which sometimes difference of two C's are trivial, and this is why you have to model out by this image. So it's not very important for us. I just want to give you a little bit of an idea of how you think of these things. But the point, what we care about is how to turn this cochain complex into a Polish cochain complex, and this is very simple, right? So all these are things that are known. I'm not doing anything. But the only thing I'm going to do is I'm going to view F as a discrete group and endow this with a product topology. View F as a discrete group and endow this with a product topology. Do the same here everywhere. So to take as a definable x, just use the product topology here. And once you have that, you have a definable version of the x bifunctor. And there is a theorem here. So, okay, because of lack of time, I guess. This definable x is a much stronger invariant than the classical x. So there are uncountably many, for example, finite rank torsion free abelian groups that have isomorphic abstract x. Uncountably means very different. also, but definable X can see the difference, right? And the rigidity again comes from the result we covered in the second part. So, yeah, I don't think I have much more time. I would like to move to check cohomology, but I think I started a little late, but I think it's yeah. I guess maybe let me attempt to say one thing here. Right. I guess I'm not sure. Well, okay. The thing is that in the case when you're trying to do like check cohomology of a space rather than a simplex, things get weird, and you have to use certain intuitions that I was hoping to have time to communicate, but I'm not sure. I don't think we'll have time. The point is that when you do cohomology for space, you start with open covers for space. Each open cover you associate a simplified complex with by looking at the intersection properties of the open sets. So your starting point for doing a check cohomology is cohomology for simplicial complexes. In the case of cohomology for simplicial complexes, the way that we turn classical cohomology to definable is very similar to in the previous slide. Basically, you just use the product topology. Like this chain complex here consists of maps from a set to an abelian group. View this abelian group as a discrete group, and you can put the product topology on all these things. Now, when it becomes tricky, so my point is this: when it comes to simplicial complexes, it is straightforward how to turn simplicial cohomology into definable cohomology. When it becomes difficult when you want to use that in the next step and define check cohomology. This is cohomology for spaces. Right. Yeah, and maybe I'll conclude with this slide, I guess. Right. So the point is that when you're trying to do check cohomology for spaces, for every space, for every locally compact space, and let's say this is a kind of abelian group. What you do is that you look at the open covers of the space, open covers of the space. So these are open sets, and to each open cover you can associate a simplicial complex called the nerve. So if you have this open set, for each open set you associate a vertex. If there is something in the intersection of these two open sets, you put an edge. If there is an intersection here, you put an edge, an edge. If there is something in the triple intersection here, you fill this up. So every time you have an open cover, you can associate a simplicial complex, and therefore take its cohomology from the previous slide. And then what you do is that as these open covers become finer and finer, this gives you a certain directed system of cohomology group which collect more and more data from how the space looks like. And in the limit, you get what it's called step cohomology. Now, there are two problems to turn this into a definable version of it. The first problem is that you cannot find a countable sequence of open covers that every open cover is defined by these things. You cannot do that. And this is important. This would have been important because, remember, if we are to put a Polish topology on these groups, we need to be able to work with separable data. So we cannot deal easily with uncountable data. We have to be able to organize them using countable remaining data, and sequences will not suffice. Still, there's a way out, but the sequences will not suffice. This is the first problem. The second problem is that the definition, as I gave it to you, it doesn't come in terms of a global chain complex. There are many chain complexes, one for each open cover, and then you have to take a co-limit. Okay, so one can deal with both of these problems, but I think the solution to the first problem is more interesting. And the solution for this first problem is basically to use the best space as a way to organize open covers. So you don't have a countable final system sequence of you don't have a countable sequence of open covers, but you have a uncountable sequence of open covers which are parameterized in a certain continuous way. So you can use separability. Basically, you have an uncountable collection to organize them, but this uncountable collection can be handled by this space which is countable. So, and I think I'll stop here.
Thank you very much for the nice series of talks. Any questions?
Yeah, so for certain nice spaces, you don't need to actually take this entire colimit in order to get check cohomology, right? You can sort of stop halfway and make the computation finite. Is the problem here, does that not work in the definable setting, or are you just trying to do this in?
It works in the definable setting, but it doesn't. Not all spaces are like that.
Right.
And so, for example, if you look at so notice docs I was talking about solenoids and homology. But at the very last minute, I told you about cohomology instead. Why was that? Well, one reason is that we have developed. I'm more comfortable with cohomology at this point because most of the data is written. But also, it doesn't really matter because homology and standard homology are dual to each other. And if whatever you do with homology, standard homology, and solenoids, the same exactly will work with homology. And if this is a solenoid, you embed it in the three sphere and you take the complement. So there's a duality. So and if you think how the torus sits inside S3, its complement can be thought as another torus. Right? Take a torus in R3, like a S3 compactified by adding a point. But in R3, think of a torus. This has a hole. This hole describes. You can pass another torus that if you put them together, they cover and you bump them up. They fill everything essentially. This is what I'm trying to say. So when you're trying to describe that, the first torus that it was in the picture here, you look at its complement, and this will give you the circle. Here, when you were taking in the section, there's a second torus that around twice. You have to think dually what this corresponds to, and what you figure out is that there is another torus that wraps also around twice, but when you think in terms of the complement, you have to add a mapping cylinder. So I guess what I'm trying to say is that this object here, is homotopy equivalent with an infinite space, like a locally compact, non-compact space, which you can construct it by adding copies of S1. And between them, add some sort of cylinders that start here with identity and here wrap around twice. Now, this turns out to be a simplicial complex. You can calculate it and make it a simplicial complex. So you can deal with its cohomology. From this using just this part. So for the main objects that we so far have applications for, we don't even go here. So this I think is like your question. You say that there are interesting spaces that you don't need to. You just need one open cover. Well, the space that we work with has a cover like that. However, we're hoping to get applications. There was another question that was asking me. Okay, we can classify solenoids using definable homology. Can you classify something classical? My point was yes, there is type of homology that classifies them. So I guess what I'm trying to say here is the following. This is a case of an object that you built it as a homotopical limit, and you can understand it in classical terms using one classical group. This is what is known as the standard homology. It's complement, the solenoid, you can understand it using the homology because it's the inverse limit of simple things. This is a homotopical limit, this is an inverse limit of simple things. However, there are spaces that are much more complex that classical things we expect them not to work, and we're hoping that for these more weird spaces, our definable invariants will work and nothing else can actually separate them. And this will be done using this set of homology, which you have to be able, not a simple open cover will suffice, but you have to, at this point in the space, you have to be able to look at the refinement at the speed, if you need to.
Yeah. So you mentioned the fact that you used some results from recent theory, and I was wondering if you've also used things like that pull from like strong determinacy assumptions and projective determinacy, or if you think that that could actually be, you could get something out of this.
We haven't worked in this direction. However, in my second talk, I discussed a little bit these topics of rigidity for Polish cover or for I talked about this P omega mod thing, this Boolean algebra thing. The people worked in this area have thought about connections like that. So there may be some connections, but we haven't explored them. But yeah, that's a good question.
Okay, maybe it's time for lunch, so let's thank guys again.